We can recognize this first problem as a limiting reagent problem because we're given amounts of both reagents. We're given 4.8 moles of NH2 and we're given 3.9 moles of N2O4. So we need to do two calculations to determine the amount of product produced if each of these reagents is consumed completely. So we need to find the appropriate mole-to-mole conversion factor for each of these reagents, and it's going to be based on our balanced chemical equation. We use our balanced chemical equation to generate both of these mole-to-mole conversion factors. We need to cancel out moles of N2H4, so 2 moles of N2H4 are equivalent to reacting 3 moles of N2. For N2O4, its coefficient is 1, so every mole of N2O4 is equivalent to producing 3 moles of N2. So we see our moles cancel out for each of these reagents, and we end up with moles of our product. In the first calculation, this results in 7.2 moles of N2. Second calculation results in 11.7 moles. We choose the smaller of the two amounts as our max product. And that's because we would never get here. We would never be able to produce 11.7 moles of N2 because we would run out of the limiting reagent after we produce 7.2 moles. So we choose the smaller of the two amounts, and that's our max product. The reagent that leads to the max product is our limiting reagent. So in this case, N2H4 leads to our max product, and that means N2H4 is our limiting reagent. The other reagent is our excess reagent. Next, we'll use our limiting reagent to calculate the amount of excess reagent that's consumed. So we start with 4.8 moles of our limiting reagent, which again is N2H4. Our mole-to-mole ratio is that every 2 moles of N2H4 will consume 1 mole of N2O4. So that means that 2.4 moles of N2O4 is consumed. Okay, we know that because we've done our math. Okay, see our moles of N2H4 cancel, and we know that 2 moles of N2O4 has been consumed. All right, so we've started with 3.9 moles of our excess reagent. 2.4 moles has been consumed. Subtraction indicates that 1.5 moles is left unreacted. In this problem, we're reacting 5.6 moles of aluminum with 4.6 moles of oxygen gas. First question is, what's the maximum moles of aluminum trioxide that can be produced? We need a balanced chemical equation. All right, we can balance this by having 2, 3, and then we'll need 4. So we have our balanced chemical equation. We're next going to do 2 calculations to find out the maximum product that could be produced from each of these individual reagents. All right, so we write down our appropriate mole-to-mole conversion factors from our balanced chemical equation. All right, so we have the appropriate conversion factors here. Moles of aluminum has a coefficient of 4, so every 4 moles of aluminum will give us 2 moles of aluminum trioxide. Every 3 moles of oxygen is going to give us 2 moles of aluminum trioxide. So we see the appropriate units cancel, and we see how many moles of our product can form from each. We choose the smaller of the two amounts, as our max product. Now we use our limiting reagent to determine how much of our excess reagent has been consumed. We know our limiting reagent is aluminum because it's the reagent that leads to the max product. That means our other reagent is our excess reagent. All right, so we've calculated how many moles of oxygen has been consumed by using the appropriate mole to mole ratio, starting with our limiting reagent. All right, so we've calculated we had 4.2 moles of oxygen consumed. We started with 4.6 moles, so the subtraction shows that we have 0.4 moles of O2 that remains unreacted.